In this video, we solved two problems from the Differential Equations quiz number 5 from the spring 2021 semester. These cover standard G18, which is the method of undetermined coefficients. Now, there were multiple forms of this quiz, so not every student saw these two problems, but on one of the forms of this quiz, both of these problems showed up as a way to assess your understanding of the method of undetermined coefficients. So for the first problem, we are asked to use the method of undetermined coefficients to find the appropriate form of y sub p. That's the particular solution. We're not supposed to solve the differential equation, and we're not asked to find y sub c. Now, normally we would have to find y sub c first and compare our initial guess to the form of y sub c to see if we have to multiply by extra x's so that some of the terms in our y sub p do not appear in y sub c. But that's not what we're asked here. We're asked not to find that. We're just asked to look basically at the right-hand side and then find the appropriate form of y sub p for this right-hand side. It's actually pretty easy. You just go through term by term and see what the appropriate guess would be. Now, this is a first degree polynomial times e to the negative 4x. So I would start with a first degree polynomial times e to the negative 4x. And here I have a first degree polynomial times cosine of 2x. So my y sub p will have a first degree polynomial times cosine of 2x plus a first degree polynomial times sine of 2x. And I'm just picking up where I left off in the alphabet here. I've got A, B, C, and D, E, and F. Okay, so that took care of this piece and this piece. Now this last piece, you don't want to think of these as separate. You want to think of this as one expression. It's a 7th degree polynomial. So I would expect y sub p. Sorry about that. There's something wrong with my connection today. Keeps dropping for some reason. I would expect y sub p to have a 7th degree polynomial as part of it. So I'll have g times x to the 7th, g h times x to the 6th, I, that's not the identity, it's a placeholder for a number, times x to the 5th, j times x to the 4th, k times x cubed, and so on, l, m, and finally n. So obviously we don't want to solve this differential equation. If we were to solve it, first we would have to find y sub c, and then we would differentiate this 3 times, substitute into the left-hand side of the differential equation, and set the result equal to the right-hand side. And then we would see, we would set the coefficients on one side equal to the coefficients on the other. Because of the linear independence of the functions, we would be able to find a system of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 equations and 14 unknowns that we could solve for our A, B, C, D, E, F, G, H, I, J, K, L, and M, and N. But obviously we're not going to do that. We're not going to solve 14 equations and 14 unknowns today, but we could use a computer to do that. It would actually be relatively simple. And then once we find the values of all of those, we plug them back in, and that would be our y sub p. Okay, so now the second part, or the second question, assessing the method of undetermined coefficients, actually asks you to use the method to find a solution of the non-homogeneous differential equation using that method of undetermined coefficients. And when I say find the solution, I guess I should have been more specific. What I'm looking for is the general solution, or a general solution of the non-homogeneous differential equation. So the way we start these problems all the time is we start by solving the corresponding homogeneous equation. The corresponding homogeneous equation is just this left-hand side equals 0. That's going to allow us to find our y sub c, and our y sub c will help us to make a better educated guess for y sub p. Now, since this differential equation has constant coefficients, we're going to let y equal e to the mx. Since it's a 4th order differential equation, we'll compute y prime, y double prime, the third derivative of y, and the fourth derivative of y. Exponential functions lead to other exponential functions. If we choose the right functions, these will cancel out and we'll get 0. So that's e to the mx, where m is a constant. If you're a student in my class, you can think of it like e to the 3x. You'd say, how do you take the derivative of e to the 3x? Well, you have e to that power times the derivative of the inside. If there was a 3x inside, I'd multiply by a 3. Since there's an mx inside, and m is just a constant, we multiply by an m. And then when you take the second derivative, you bring your constant down, and you take the derivative of e to the mx again. We get e to the mx times the derivative of the inside, which is just another m. That m times that m gives you an m squared. So every time we take the derivative, we end up getting another m. That extra m comes from the chain rule. It's the derivative of the inside for that exponential function. So those are our y, that's our function y, and all of y's derivatives there. Now we want to substitute these into the differential equation. It's going to lead to an algebraic equation that m must satisfy if y equals e to the mx is actually a solution to this equation. So we'll have the fourth derivative of y with respect to x, excuse me, minus the second derivative of y with respect to x equals 0. And we can factor out the exponential. And we've got a product equals 0. The only way a product equals 0 is if this factor equals 0 or this factor equals 0. Exponentials are never 0, so we have this polynomial equation. This polynomial must be 0, and that's called the characteristic equation or the auxiliary equation of our differential equation. And then you can just solve this however you like. I see a greatest common factor, so I'll start by factoring out an m squared. M squared times m squared would give me an m to the 4th. Then I ask myself, m squared times what would give me the negative m squared? That's a negative 1. This is a difference of squares, so that factors to m plus 1 times m minus 1. So our characteristic equation has been factored as much as possible. We just set each of those factors equal to 0 and solve for m to find the roots of our characteristic equation. So we have m squared equals 0, which means m1 and m2 are both 0. Now, the reason I have 2 values of m associated with that is because that's squared. You can almost think of this as an m minus 0 squared. Then on this guy, I've got that. If I subtract subtract 1 from both sides, I get m equals negative 1. That's our third value of m, so I'll call that m sub 3. And then I'll take this guy, set that equal to 0, and add 1 to both sides. Since it's our fourth value of m, we'll call that m sub 4. It was a 4th degree polynomial, so I have 4 roots. One of them happens to be repeated, then I have this third, and then I have the 4th. If you happen to get 3, if you get this one and this one and this one, and then you look back here and you see it's a 4th order, or you look here and you see it's a 4th order differential equation, or you look here and you see that's a 4th degree polynomial, you know you missed something, and it's usually something like a repeated root. Okay, so we found our values of m, and then each of those corresponds to a solution of the differential equation. So for y1, we have e to the m1x. Well, that's e to the 0x, e to the 0 is 1. For y2, since it's a repeated root, we take this solution and we multiply by an extra x. It's still x times e to the 0, so it's just an x. Then over here, this is a distinct real root. y3 will be e to the m3 times x, so it's going to be e to the negative x. And y4 will be e to the m4 times x, which is e to the 1 times x. Remember, with a repeated root, you multiply by an x. If it was repeated 3 times, I'd multiply by an x here, and then I'd multiply by an x again. And then if you have distinct roots, you just get e to the mx. Sorry about that. I don't know what's going on with my document camera today. It's a little finicky. Just keeps cutting out. All right. And then the general, well, not the general solution, the general solution of the homogeneous equation. We call that y sub c. Since it's fourth order, we have c1y1 plus c2y2 plus c3y3 plus c4y4. And in our case, we've got y1 equals 1, y2 equals x, y3 equals e to the negative x, and y4 equals e to the x. Easy breezy. You just multiply your 4 linearly independent solutions by constants, and then you add them together. And that is the solution to the corresponding homogeneous problem. Now let's go back to the non-homogeneous problem. We've got the fourth derivative of y minus y equals 4x plus 2x times e to the negative x. Now the way we start this problem, or the way we start this part of this problem, is we state the educated guess for y sub p that we would make if we didn't know anything about y sub c. So I'd say for this term, I have got a first degree polynomial. So I would use ax plus b. I would assume y sub p has a first degree polynomial in it to account for that piece. Then over here, I would say that's a first degree polynomial times e to the negative x. So that's going to give me a first degree polynomial, cx plus d times e to the negative x. Now I have to ask myself, like, are there any terms on this list that are on this list? Because remember, if y1 is a solution to the differential equation, the homogeneous equation, if you multiply by a constant, it's still a solution. If y2 is a solution, then a constant times y2 is a solution. So this is a solution to the homogeneous equation. So is this, so is this, and so is this. Which means if I plug in something that looks like this into this equation, I'm going to get 0. Or something that looks like this, or something that looks like this, or something that looks like this. Like for the example with the constant. Obviously, if I take the second derivative of a constant, I get 0. And I'll have 0 here and 0 here. 0 minus 0 is 0. So this is a solution to the corresponding homogeneous equation. Okay, so the question becomes, with that in mind, the question becomes, look at your y sub p. Is there any term on this list that's already on this list? If it's on this list, it's not going to give us anything that we want on the right-hand side. When we substitute into this left-hand side, we're going to get 0. We're not going to get a 4x or a 2x times e to the negative x out of it. Well, look at this. I've got an ax plus b. A constant times x is a solution to the homogeneous problem. And a constant by itself is a solution to the homogeneous problem. So you might say, okay, this is on this list, and so is this, so I'll multiply by an extra x. But if I distribute, then what do I have? I have ax squared, not on the list, so that's fine, plus bx. But a constant times x is already on this list. So multiplying by x is not enough. We need to multiply by x squared here. Because if I take ax and I multiply by x squared, I get ax cubed, and that's not on this list, which means this ax cubed is not a solution to the corresponding homogeneous problem, which means when I plug in ax cubed, I'm not going to get 0. And I don't want to get 0. I'm hoping to get something related to that 4x there. And then b times x squared is not on this list, so that's good. That's our modified educated guess for this 4x, given that this constant and the constant times x is part of our y sub c. Okay, so over here, we're going to do something similar. You say to yourself, okay, this is a cx times e to the negative x, or a constant times x times e to the negative x, and a constant times e to the negative x. You ask yourself, are there any terms on this list that look like that? The individual terms that are associated with this piece. Well, I don't have a constant times x times e to the negative x on this list, but I do have a constant times e to the negative x. That d times e to the negative x, if I substitute that in over here, it's going to cancel. The derivatives will cancel and I'll get 0. And I'm not trying to get a 0. I'm trying to get this 2x e to the negative x. Since the d times e to the negative x a constant times e to the negative x is in the y sub c. We're going to multiply by x. Now think about what happens. We get cx squared times e to the negative x. A constant times x squared times e to the negative x is definitely not on that list. And then for this guy, we say d times x times e to the negative x. Is that on the list? It's not because of the x. So this is going to be a good guess. I would recommend distributing that x squared and that x to the polynomial first before trying to find your a, b, c, and d. Okay. Okay, so we've made our educated guess for y sub p. Keeping in mind y sub c and modifying as necessary. Now I recommend you distribute x times x is going to give me an x squared there. D times x is there. I'm going to keep that exponential on the outside. All right. Now we're assuming that this function is a solution to this equation for some values of the constants a, b, c, and d. We call this the method of undetermined coefficients because y sub p has undetermined coefficients in it. The undetermined coefficients are the a, the b, the c, and the d. We're going to try to find them. In order to find them, we assume that this is a solution to this problem. We take the derivative 4 times, we plug it in, and then we set the expressions on the left-hand side equal to the expressions on the right-hand side. So the next thing that we need to do is compute y sub p prime. This is a polynomial. It's easy enough to take that derivative. The derivative of a constant times x cubed is that constant times, well, you bring the power down and you multiply by x to the 1 less power. Over here, we bring our constant b down and you take the derivative of x squared. Bring the constant down, that's a 2, multiply by x to the 1 less power. Now over here, I've got a product of 2 functions, so I will use the product rule. According to the product rule, the derivative is the derivative of the first, just using the power rule for each of those, times the second, undifferentiated, plus the derivative of the second, derivative of e to some power is e to that power, times the derivative of the inside, times the first. And I would recommend factoring out that e to the negative x over here. So I've got 2cx plus d, and then over here I have a -1 times this. So -1 times cx squared and -1 times dx. And all that's multiplied by an exponential. And I will reorganize those terms at the very end. Let's put our quadratic term first. And then I want x terms. I've got 2cx minus dx. So that's 2c minus d times x plus d times the exponential there. All right. That's y sub p prime. We want y sub p double prime next. Just use the power rule here. 2 times 3a is 6a times x to the 1 less power. The derivative of a constant times x is just the constant. Here's my first function, and here's my second function, and I'll use the product rule. According to the product rule, we have the derivative of the first times the second undifferentiated, plus the derivative of the second, derivative of e to some power is e to that power, times the derivative of the inside, times the first. Okay, and again, it's a good idea to collect like terms. All right, so I'm going to grab these in the order that I want. I wanted my x squared term first, then my x term, and then my constant term. So here's my x squared term. I've got negative cx squared times the -1, so it's going to be a positive cx squared. And then for the x term, I have a -1 times 2c minus d. So that will be, a -2c subtracting a negative d is going to be adding d times x for that piece. And then we've got negative 2c times x there. Okay, and then we've got the constant term. I've got 2c minus d minus another d, so that's going to be 2c minus 2d times, whoops, sorry about that. My document camera is being finicky today. I have no idea why. Got 2c minus d minus another d. That's 2c minus d times our exponential function. Okay, that was y sub p double prime. We've got to go up to the fourth derivative, so we got to keep going. Y sub p triple prime. The derivative of a constant times x is just the constant. Derivative of the constant by itself is 0. Here we need the product rule. There's our first function, and there's our second function. Actually, this can be combined. We can write this differently. We've got negative 2c minus 2c, that's minus 4c plus d. So we have derivative of the first. So it's going to be 2cx plus this constant times x. We'll just get the constant. Derivative of that piece, derivative of constant is 0. That's derivative of the first times the second plus the derivative of the second, which is that negative e to the negative x again, times the first. And I'm using the simplified version, negative 4c plus d times x there. Okay, let's collect like terms. I want my x squared term first. I have a negative 1 times cx squared. So it's going to be negative cx squared. And I want my x terms. I've got a 2cx there. And then I'm subtracting a negative 4c plus d times x. So 2c minus a negative 4c is going to give me a 6c. And then I have negative 1 times d. There we go. Those are my x terms. And then the constant term is negative 4c plus d minus this. Negative 4c minus 2c is going to give me a negative 6c. And d minus a negative 2d, that's going to be d plus 2d, that's going to give me 3d times our exponential. All right, that was y sub p triple prime, y sub p to the fourth, or not fourth, but fourth derivative of y sub p, excuse me. Derivative of constant is 0. Last product rule. Here's our first function, and there's our second function. So we have the derivative of the first times the second plus the derivative of the second times the first. Okay, and we want to collect like terms again. Negative times a negative is going to give me a positive 6cx squared. Now x terms. I've got a negative 1 times cx, or 6c minus d times x. So that'll be negative 6c minus 2c times x. It's going to be negative 8c times x. And we're subtracting a negative d, so it's going to be adding d times x. All right. And then for the constant part, I've got 6c minus d, and we're subtracting this. 6c minus a negative 6c is 12c. And then we have negative d minus 3d is minus 4d. And that's all multiplied by this exponential. So we had our third derivative and our fourth derivative. Now we want to substitute these into the left-hand side of the differential equation and set the result equal to the right-hand side. Because of the nature of these, because there's so many terms, I think it's helpful to add these vertically instead of, or subtract vertically. Like if you were in elementary school, sometimes you'd have flashcards that would say 5 minus 3 equals 2, and they would look like that. That's exactly what we're going to do, but with the fourth derivative of y and y, or the fourth derivative of y sub p and y sub p itself. We'll stack vertically and we'll have like terms in columns, and that'll make the bookkeeping a little bit easier. So first, we're substituting into the differential equation now. We've got the fourth derivative of y sub p. And then we're subtracting y sub p, and y sub p was this. So I'm just going to multiply by -1. Oh, sorry. That's not right. We're subtracting y sub p double prime. I wrote that down wrong. Here we go. So I'm just going to take y sub p double prime, which is on this line, and I will multiply it by -1. So every term will get multiplied by -1, and then I'll write that down here. So I'm actually focused right here, and I'm multiplying by -1. So I've got a -6a times x and a -2b. And then here, I'll have a -cx squared. If I multiply this by -1, this version by -1, I'll have positive 4c minus d times x. And then this one will give me a -2c plus 2d times the exponential. And then we just add. These guys reduce, these guys reduce. Okay, and so we have -4c times x plus 10c from this column minus 2d. All of that is multiplying e to the -x. And then we have the -6a x minus 2b. We're going to set that equal to the right-hand side of the differential equation, which was 4x. I'm going to line up the like terms here, my x term with my x term, plus 2x, I guess plus 0, times e to the -x. Okay, so if you want, you can do that. All right, so x times e to the -x, e to the -x, 1, and x. Those are all linearly independent functions. There's no combinations of 1s, x's, x e to the -x, and e to the -x that you could. There's no combination of 3 of those that would allow you to find the third. So they're linearly independent from each other. What that means for us is that if the left-hand side equals this and the right-hand side equals this, the only way that happens is if the corresponding coefficients are equal. So the coefficient of x e to the -x on this side, which is -4c, must be equal to the coefficient of x e to the -x on this side, which is 2. And then this coefficient of e to the -x, 10c minus 2d, must be equal to the coefficient of e to the -x on the other side, which is 0. And then -6a must equal 4. And -2b, that's our constant term on the left, must equal the constant term on the right, which is 0. So we've got 4 equations and 4 unknowns, but they're pretty simple equations. So we can just take each of these and solve. This one's the easiest. Divide both sides by -2 and you get b equals 0. Here, if we divide both sides by -6, we have a equals -6 or -4 over 6. Divide the numerator and denominator by 2 and you get that. Over here, we have c equals -2 over 4, which is -1/2. And if we substitute in -1/2 here, we've got 10 times -1/2, which is -5, minus 2d equals 0. So that means that -2d must equal +5, so d must be equal to -5 over 2. Okay. So what did we do here? We substituted into the differential equation. And then we set the left-hand side equal to the right-hand side. And that led to a system of 4 equations and 4 unknowns. Then you just solve for the unknowns. And once you have the unknowns, what that tells us is that if A, B, C, and D take on these values, then this function y sub p is a solution to that differential equation. So we just substitute in our A, B, C, and D to this, and that'll be our y sub p. So y sub p was a times x cubed, and a was negative 2/3. So I've got negative 2/3 x cubed plus b times x squared. B is 0, so that's gone. Plus cx squared, so that's negative 1/2 x squared, plus dx, and d was negative 5 halves, negative 5 halves, excuse me. That's times x. We're multiplying that by our exponential function. And that's our y sub p, and of course the general solution is what we're looking for. Y is equal to y sub c plus y sub p. Make sure you label that function. Don't just write y sub c plus y sub p. We want to know that its name is y, and y sub c was c1 plus c2x plus c3 e to the negative x plus c4 e to the x. And then y sub p was this expression that we just found. And you could just write minus 2/3 x cubed. In hindsight, I probably would have done that. Okay, I really want to simplify this. So let's simplify. So we have minus 2/3x cubed. Maybe factor out a negative 1/2. Negative 1/2 times x squared plus 5x times e to the negative x. I guess you could factor out the x as well if you wanted to. And that will work. That'll be your solution for all real numbers.